So the next speaker is Michele Botti from Politecnico, right?
Yes, exactly.
From Politecnico of Milano. And his talk will concern non-conforming polyhedral discretization methods for multiple network poroelasticity. Please, Michele.
Thank you for the introduction, and thanks to the organizers for these nice 3 days of interesting talks. So what I will present is a joint work with my brother Lorenzo and Daniele Di Pietro. And it's part also of the research activities of the project PDEs that is funded by the European Union in the framework of Marie Curie International Fellowship. So I will discuss the discretization of the multiple network poroelasticity problem that describes seepage through fissured porous media. But to start, let's first of all see what are the Biot equations that were introduced in 1941 by Biot. So we have two coupled equations. In the first one, we have mechanical equilibrium, and in the second one, the conservation of mass. 20 years later, more or less, Barenblatt proposed another model for describing the porous media flow when there are more than a single network, a single pore network. So in particular, the case in which we have two different pore networks with different porosity and permeabilities. So in this case, more or less, the system is the same. Of course, we have an additional equation, but we have also mass transfer contribution in the second and in the third equation here. Then we can generalize this idea to also deal with a general number of pore networks, and as a result, derive the multiple network poroelasticity equations. So here we can see that in the mechanical equilibrium equation, the first equation, we have the contribution from all the pore pressures networks. And again, in the second equation, we have these exchange terms that appears. And so we have the coupling between the two equations here, and each of the Darcy equation in the M networks are coupled together. So we are mainly interested in geoscience applications, such as CO2 storage or geothermal energy production, for instance. But there are other notable applications in biomechanical field, such as, for instance, brain modeling. In this framework, we very often have to deal with different type of geometries and also very complex ones. In particular, we can have, as shown in this picture, different layers, different pore networks, and also some interfaces in the domain, which models fractures. Okay, so what about the formulation and the discretization that we want to analyze? We consider the total pressure weak formulation that consists in introducing an additional variable to the system, which is the pressure P0, the total pressure that is obtained in this way. So we have the contribution coming from the dilatation of the porous material and the contribution related to each of the different pore pressures. Okay, by introducing this additional variable, we have an additional equation, which is the second one. And we can observe that the first two equations are coupled together, while the Darcy's equation are coupled, but we don't have the displacement appearing here. Okay, so let's say that we have change the way the equations are coupled. And another interesting features of this formulation is that this time we have the Lamé coefficient, the dilatation coefficient, which appears here in the second equation, and this facilitates when we want to derive locking-free methods. So this idea is also used very often recently, also for the single network problem. Okay, so what we will study for the analysis is the case of an implicit time discretization method, for instance, implicit Euler. The elasticity operator will be discretized by the hybrid high order method. And for the Darcy operators, we have two choices in mind. One is to use again the HHO method, and the second one is to use a symmetric weighted interior penalty discontinuous Galerkin method. Okay, first of all, before going into the details of the methods, let's see which are the features of these two methods. First of all, they can support general polyhedral meshes. As we have seen, it's a crucial feature. Then we have a formulation of the problem that is independent of the spatial dimension and on the number of networks that we are considering. We have an substable hydromechanical coupling. The discretization that we obtain is robust, both respect with the quasi-incompressible limits and with the case of low permeable and heterogeneous media. The analysis that we have derived can treat the case of incompressible grains that corresponds to storage coefficients equal to 0. We have also, we can formulate an alternative discrete problem based on equilibrated traction and fluxes, and this is, can be useful, for instance, for a posteriori error analysis. And finally, we have a robustness also with respect to pressure or oscillation. Okay, so yesterday we have seen from the presentation of Professor Ern the detail about HHO methods, so I can go faster. What about the discrete spaces? So they are depicted here. We have modal degrees of freedom attached to faces and cells. And because it will be useful later, we also introduce this interpolator that is just given by L2 projection on cells and faces. Using these degrees of freedom and inspired by an integration by parts formula, we can reconstruct some operators. First of all, the strain reconstruction that is given by this formula, in which, of course, interior degrees of freedom are considered when integrating on the cell, and phase degrees of freedom are placed here when integrating on interfaces. From this definition, we can prove easily that we have this commuting property that is actually the crucial property for the analysis. And by taking the divergence reconstruction simply as the trace of this strain reconstruction, we get the same commuting property also for the divergence. We can also reconstruct a higher order displacement. So in the space of polynomial of degree k plus 1, when considering polynomial of degree k on the cell and on the faces, it is the elliptic projector operator with respect to this scalar product here. And as a result, of course, we have optimal approximation properties. So the first version of the HHO scheme that was derived by Daniele Di Pietro and Alexandre Erne in this paper is given by this operator here, where we can notice that we have the usual stabilization. I would like also to discuss briefly some of the variants of this operator. First of all, for nonlinear problem, in order to have a sequential consistency property, is useful to replace the gradient of the displacement reconstruction with the strain reconstruction here. So it's a larger reconstruction of the strain, let's say. And stabilization is, as usual, given by penalizing phase-based residual. But the important feature is that we want these two properties to hold. So, of course, coercivity and, let's say, polynomial consistency up to degree k+1, because we don't want to lose the accuracy of this higher order reconstructions operator. So we have another variant of the method that is meant to use also the case of piecewise constant polynomials on the cell and on the faces. Why we have to, let's say, hack the original scheme? Because we can see that these two properties are incompatible when considering k equal to 0. Because actually rigid body motion are linear functions. So we cannot have a vanishing stabilization that gives coercivity, because we have rigid body motion in the kernel, of course. So our simple idea to treat this case was to add another penalization that is obtained in a DG way, let's say. So we penalize the jumps of the displacement reconstruction. And why it can be useful to have the low order version of the method? Because as we have seen yesterday, we can have some problems with less regularity. In particular, for instance, here we have a singularity in the origin. And in this case, Lorenzo Mascotto yesterday has shown that we cannot achieve the full order of convergence. Maybe we can try some strategies like enrichment, as he has shown yesterday. But if we want to stick with a polynomial function, at least from the convergence viewpoint, there's no meaning of going a higher order if we cannot do better than this. Okay, what about the hydromechanical coupling? Using the property of the divergence reconstruction, we can show that we have an in-sup condition. And actually, it is very straightforward to prove this result, because the interpolator is a Fortin operator. We have continuity, and since we have also commutativity of the divergence, we have this property. The Darcy term can be discretized by the HHO method or by the DG method. The discretization with using HHO is actually the same derivation, but with scalar valued function instead of vector valued ones. And so I can skip it. What about the DG method? So in this case, we have a classical interior penalty method in which we are considering weighted averages here. And as penalty parameter, we take the harmonic average of the two permeabilities when we have jumps. So this is quite classical. So let's move on with the main results. So the first concerns actually the single network case, and is mainly derived in this work here. So first of all, we were able to prove a regularity estimate, and requiring regularity only on the data. And with this, exploiting this regularity, we were able to prove abstract a priori estimate. By abstract, I mean that we introduce an abstract framework in which we can then apply these results also for other schemes, for instance, HDG or non-conforming virtual elements, and so on. In our analysis, we applied this framework to of HHO and HHO-DG discretization. And we also perform some comparison of the two. What about convergence for the multi-network case? So in which we have arbitrary number of pore networks. So introducing, of course, optimal projections on the discrete space, we can prove this result. So we have the L infinity norm in time of the strain norm of the displacement and the L2 norm of the pressures that is bounded by this quantity here. And we can observe that we have the optimal expected convergence order of the HHO scheme, that is h to the power k plus 1. The time step tau, here we have a linear dependence because we are considering first order time marching scheme in this case. An important remark is that so this theorem holds for both the proposed schemes, but actually for the HHO DG case, we need to assume elliptic regularity for the Darcy problem and k greater than 1. An important feature of this estimate is that even when the storage coefficient are equal to 0, we still get a bound of the pressure errors. So let's move to some numerical results. We consider the Biot-Barenblatt problem, so 2 networks. And to assess robustness, we consider 4 sets of model coefficient. So in the first one, we have a reference situation. In the second one, we have a very large Poisson ratio. In the third, we have vanishing storage coefficient. And in the last one, we have low permeable, the low permeable case. What
Michele, you have a couple of minutes left.
Okay, thank you, Alessandro. So what we observe is that in all the cases, we get the expected convergence order. We did this in both for different polynomial degrees, and these are the results. So everything works fine, at least on this manufactured solution. A more application-oriented test consists in these 2 network pore-elastic footing, in which we are applying a load surface here. And this time we are interested in 2 cases, let's say, one in which the exchange term is exchange coefficient is equal to 0, and one in which is equal to 1. And what we observe is that, of course, when we have this mass exchange term, the 2 pressure resembles more. Okay, let's say this. So to conclude, what we have done is analyzed and tested these non-conforming polyhedral schemes for this multiple network pore elasticity problem. And of course, there are many things still that can be improved. For instance, we can think about better solvers, so using splitting schemes or multi-grid methods. And then we can also generalize the discussion to nonlinear flow models or fracture media, and also thermopore elasticity, if we want to consider the application to geothermal energy production. Thank you very much for the attention.